Hi, I'm Molly Egan. I'm a sustainability and energy analyst at Cause, supporting the Snow Krylik Architects design team on the design of the new Graco Park building. We wanted to take this opportunity to walk through the building performance, sustainability strategies, and goals for this project. The new Graco Park building is targeting net zero energy performance. Net zero energy buildings are defined as ultra-low energy consuming projects that consume only as much power as can be generated on site by clean renewable resources. Net zero is a critical goal for our era of climate change because net zero buildings support the decarbonization of buildings and the transition to an all-electric grid powered by renewables. They do this by significantly reducing carbon emissions from operational energy use, day-to-day energy use. Also by contributing to the actual renewable energy sources available, in our case, a roof-mounted photovoltaic system. And also by introducing no new fossil fuel-based energy demands. So not using fossil fuels for space heating, hot water, and appliances, but rather using all electric sources. Net zero energy is recognized worldwide as one of the highest aspirations in energy performance that a building can achieve. And it's critical that an increasing number of buildings built today strive to achieve this goal to minimize or eliminate carbon emissions attributed to operating buildings over their lifespans. This goal requires a truly integrated design team, and building performance analysis has been interwoven into the process throughout all stages of our design process, in order to identify and implement the most impactful strategies for achieving this deep level of energy efficiency. Let's break down the process and energy efficiency strategies that have been incorporated to pursue this target. A very first step in our analysis process was to get an understanding of where and how energy is being consumed on this project, given its unique size, building type, and location. We refer to this as a baseline energy analysis, and the results of this study serve as a way for us to compare the impact of our energy efficiency strategies against an unoptimized version of the project. This study also serves as a really helpful wayfinding tool for understanding which energy efficiency strategies will have the most impact on building performance, so we can prioritize those specific strategies. So using the same project size, location, space types, and internal loads, the total estimated energy use of this project before any energy optimizations are implemented would be roughly 88 kBTU per square foot per year. And this value is referred to as the energy use intensity. This is far more energy than could be reasonably supported with on-site renewable energy, so we need to take steps to reduce this baseline energy use. In the inner ring of this graph is a breakdown of the major energy end uses for this building, including heating, cooling, equipment, snow melt, and hot water. We can see that energy needed for heating throughout the year is the biggest use in cold climate Minnesota, followed by energy needed for internal equipment and lighting, and smaller uses for hot water, cooling, and snow melt. The outer ring of this graph is the most insightful because these results allow us to identify the specific building characteristics which are most greatly contributing to our overall energy loads. The largest slices of this outer ring represent the biggest opportunities to dramatically reduce energy use, and they're unique to each individual project and location. With this insight in hand, the design team was able to focus on implementing the highest priority strategies to reduce energy use. In the case of Graco Park, these strategies included reducing heat loss through the mechanical ventilation, reducing heat loss through windows, reducing heat loss through air leakage, or what's known as infiltration, using high-performance envelope assemblies, meaning high levels of insulation in the roof, walls, and under the slab, and also utilizing efficient all-electric space conditioning systems. Through these key optimizations, estimated overall energy consumption for the proposed building is now reduced by roughly 75% compared to our original unoptimized condition. This level of energy efficiency is targeted specifically because it's equivalent to the estimated renewable energy production of the roof-mounted solar voltaic array, bringing the Graco Park project in line with achieving net zero energy. Now let's take a look at the various energy efficiency strategies that are bringing us in line with the net zero energy goal. The graphic you see here steps through the various energy efficiency strategies that are bringing the design in line with the goal of net zero energy. The order in which we consider these strategies is important, focusing in first on passive design strategies that cost little to nothing to implement, and then optimizing the details of the project that we identified as high priorities in our first energy analysis, before finally sizing and selecting advanced mechanical systems. The design process began with a focus on optimizing passive strategies, such as the overall form and orientation of the building, to reduce energy consumption with approaches that introduce little to no additional project cost. The Graco Park building is oriented on the site so that the longest sides of the building are south and north facing. East and west facades are difficult orientations to control solar glare, and glass on these sides can also result in overheating due to low sun angles, if not properly shaded. Elongating the south facade allowed the design team to have better control over when direct sunlight enters the building. This allows beneficial low-angle winter sun to enter and help heat the building during the coldest times of year, while easily blocking the high summer sun angles with strategic shading devices to avoid overheating. In addition to having an energy benefit, placing a higher percentage of windows on the south side of the building also helps to provide well-daylit spaces throughout the year. Strategically placed windows on all sides of the building allow even daylighting while creating a dynamic interior environment. And the overall exterior expression of the building's wood slats and extruded west porch are designed to control glare passively during times of the day and year that have the most challenging sun angles. In early design, the team also used energy and envelope analysis to identify the proper amount of insulation to use in the exterior walls, the roof, and also under the slab. What's interesting about these studies, which analyze the impact of different levels of insulation on overall energy use, is that we can actually identify a point of diminishing returns as insulation depths get thicker and thicker. While in cold climate Minnesota, well-insulated assemblies are a key strategy for high-performance buildings, we also want to make sure that we're not over-insulating beyond a point that is really moving the needle on building performance, and that the project budget is being spent in places that are actually impacting building performance and we're not overdoing it. For example, in our exterior walls, we're able to identify that there was less return on investment with a depth of insulation greater than 6 inches of exterior insulation plus the cavity insulation. The design team was then able to use the findings of these studies to design wall, roof, and floor assemblies that could meet the targeted thresholds of building performance and also compare the differences between these different assemblies. Most assemblies on this project required roughly twice the thermal performance that would be required by energy code values in order to meet the net zero design standards. Building air tightness is an often overlooked strategy for high-performance buildings because heat loss due to air leakage is invisible. But the impact of air leakage is made obvious to us through the findings of our energy simulation, which indicate that air leakage, also referred to as infiltration, is one of the primary ways that this project would lose heat throughout the year. This is a common problem for buildings in cold climates, and it's especially true for buildings with large ratios of exterior wall to floor areas like we have at Graco Park. But these heat losses can be mitigated by detailing and constructing the building to have a continuous air control layer across the entire building envelope. The roof and exterior walls of the Graco Park building are designed to include an interior service cavity, where the majority of pipes, wires, and other services can be run through to minimize the number of holes that need to be punched through this air control layer, which is protected on the other side of that interior service cavity. The design and detailing can only go so far in ensuring proper air sealing of a building. It's important to also ensure quality construction of this air control membrane by communication with the contractor and also obtaining the services of a building enclosure commissioning agent. This enclosure commissioning agent plays a critical role in identifying potentially problematic conditions in the building enclosure while they can still be fixed during construction. and also performing on-site testing to verify that the project is on track to achieve its intended air tightness target necessary to achieve net zero energy. Another invisible but highly impactful energy efficiency strategy is the use of heat recovery ventilation. The mechanical design of this project includes a ventilation system called a dedicated outdoor air system, DOAS, which provides continuous, fresh, filtered ventilation to the interior spaces. These systems lose only minimal energy because the exhaust airstream leaving the building exchanges its heat with the incoming fresh air to recover around 80% of the total heat through an almost passive system design. The exhaust and supply airstreams never cross, so there's no contamination of incoming air, making heat recovery and DOAS ventilation systems highly efficient and a key strategy for providing extremely high levels of indoor air quality and continuous ventilation with very low energy consumption. Last but not least, after the building energy loads have been significantly reduced through the strategies we've discussed, the use of highly efficient space heating and cooling mechanical systems allows the building to reduce actual energy consumed dramatically compared to a conventional system. At Graco Park, the remaining space conditioning needs are met through a geothermal well system adjacent to the building, which takes advantage of the stable temperature of the earth throughout the year to provide highly efficient heating and cooling through a radiant floor system. A typical modern natural gas boiler has a heating efficiency rate of about 90%, whereas a geothermal heat pump system has heating efficiencies of over 300%, making them 3 to 4 times more efficient than a conventional heating system. In this way, the remaining heating demand is nearly quartered, and cooling demand is reduced as well. It's important to prioritize all other energy efficiency strategies before designing and sizing advanced mechanical systems. This is because reducing the overall building loads, as we've done by over 50% before HVAC systems impact, will in turn reduce the overall required size of the mechanical systems themselves. This makes expensive space conditioning systems like geothermal and other heat pumps significantly more affordable because they're smaller systems. Finally, by having all building operations at Graco Park use electricity as a source fuel, further reduces operational carbon emissions in 2 different ways. First, as the utility grid continues to phase out fossil fuels, Graco Park will be poised to support the transition to renewable energy. And secondly, by having an extremely high efficiency building, overall energy use and the associated carbon emissions are reduced in general, meaning no matter how long it takes to transition our local utility grid, Graco Park will be supporting decarbonization by reducing demand. Now, bringing this all back to the net zero goal, let's take a look at how we determined what the energy consumption target would be based on renewable energy feasibility. The overall energy performance target of the building is determined by the amount of renewable energy that can be harvested from the photovoltaic array located on the south-facing slope of the building's roof. For this project, about 47,000 kilowatt hours of electricity per year can be captured with PV panels on the roof. Therefore, our annual building energy usage cannot exceed this energy budget in order to achieve net zero energy status over the course of the year. There will be times of year, such as during milder spring and fall conditions, in which the PV array is producing more energy than the building is using. And there will be other times of year that the PV array is producing less than the building energy demand, such as during the winter when energy use is highest because of heating energy. However, because the building will be tied into the electrical grid and net metered, the objective with net zero energy design is for the building to consume an equivalent amount or less energy than the PV array produces on a net annual basis. As we continue in the final design stages, we have the opportunity to refine some of the details that impact energy use and also evaluate the best balance of building performance strategies in regard to overall project cost. Some of our primary next steps and recommendations for this phase are: 1, to refine our assumptions for internal building loads, such as lighting and any plug-in equipment. Lighting and equipment selection process should have the net zero energy target in mind, and we recommend selecting high efficiency lighting and Energy Star rated equipment for all appliances and computers. We'll also be checking our assumptions for how the building is expected to be used to ensure our energy models are reflecting this understanding. An energy model is an estimate and will never be a perfect predictor of reality. However, we'll be working to build in the most true picture of how the building will be used, since this is a significant factor in overall energy use and will help us determine the best smart building strategies, such as automatic occupancy and lighting controls. We also recommend obtaining the services of both an HVAC and building enclosure commissioning agent to review the final drawing set and specifications and develop a quality control and commissioning and testing plan for the construction phase. The high-performance design of the new Graco Park building is an accomplishment that the Minneapolis Park and Rec Board deserves to be proud of. We're looking forward to continuing on the next steps to achieve this goal.